From the thunderous roar of early jet engines with simple centrifugal compressors and can-type combustors, to today's fuel-efficient high-bypass turbofans, jet propulsion has come a long way. In this video, we'll trace the fascinating evolution that shaped modern aviation power. Good day, everyone. Let's journey back to the dawn of the jet age and look at a simplified replica of one of the very first engines to take flight. At the very front of this engine begins the process of jet propulsion, with a centrifugal compressor that draws in air and flings it outward at high speed, raising its pressure before directing it into the combustion chambers. Surrounding the impeller is a diffuser, the outer ring of the compressor, where the high-velocity air slows down and its pressure increases further, ensuring a steady, high-pressure flow into the combustors. Next, the compressed air enters a ring of can-type combustors, individual chambers arranged around the engine. Each can have its own fuel injector, igniter, and perforated liner, operating almost like a set of miniature furnaces. As we open one of these cans, we can see the perforated liner inside. These tiny holes carefully control how the air mixes with the burning fuel, helping to anchor a stable flame near the front, while preventing it from being blown out by the high-speed airflow. Once combustion is complete, the high-energy gases rush toward the turbine at the rear. The turbine's blades extract just enough energy to keep the compressor spinning, sustaining a continuous cycle of intake, compression, combustion, and exhaust. Finally, the remaining gases expand to the nozzle to produce the jet thrust that propelled early turbojets into the sky. It was a simple, elegant system, where every stage depended on the other, and perfection in balance meant flight. After the single-stage centrifugal compressor, engineers developed two-stage centrifugal compressors. Air leaving the first stage is denser due to the initial compression. The second centrifugal stage is therefore slightly smaller in diameter, designed to further compress this denser air efficiently. This staged approach increased the overall pressure ratio of the engine, enabling more powerful and higher-performance turbojets. While engineers were refining centrifugal compressors, simultaneously another type of compressor was developed, the axial flow compressor. Unlike centrifugal designs, axial compressors compress air through multiple stages of rotor and stator blades, arranged along the engine's axis. Each rotor blade pushes the air backward, while each stator blade redirects and guides it to the next stage. Visually, this can be represented by the gradually decreasing diameter of the duct through which the air flows. As the air is pushed backward stage by stage, it becomes progressively denser and more pressurized. One major advantage of axial flow compressors is that they can achieve significantly higher overall compression ratios than centrifugal compressors. Following the compressor, the air enters the annular combustor, the successor to the can-type combustors. Here, maintaining a steady flame is crucial. A diffuser slows the incoming high-speed air, while the perforated liner ensures proper mixing and prevents the flame from being blown out, much like a candle protected from wind. A fine mist of fuel sprays into the liner through the nozzles, igniting into flames that ultimately produce the engine's thrust. The combination of all these factors maintains a continuous and stable flame and combustion efficient. Finally, the high-energy gases flow toward the turbine. The turbine extracts energy to drive the axial compressor, completing a continuous cycle of intake, compression, combustion, and exhaust that powers the engine forward. After the development of single-stage axial flow compressors, engineers sought ways to achieve even higher compression ratios without making the engine excessively long or complex. This led to the design of two-stage axial flow compressors. In this arrangement, air first passes through the initial set of rotor and stator blades, where it is compressed to an intermediate pressure. Then, instead of continuing at the same rotational speed, the second set of blades can be designed to rotate at an optimal speed. By doing this, the denser air entering the second stage can be compressed even further, achieving much higher overall pressure ratios than a single-stage axial compressor could. This staged approach offers many advantages. For example, higher overall compression. By tailoring the rotational speed and blade geometry of the second stage, engineers achieved higher pressure ratios than was possible with a single stage. Now, we move to the turbine stage of our two-stage axial flow compressor engine. Here we have two turbines, the high-pressure turbine highlighted in red and the low-pressure turbine highlighted in blue. These turbines are connected to two independent concentric shafts. The high-pressure turbine drives the high-pressure compressor via the outer hollow shaft, while the low-pressure turbine drives the low-pressure compressor using the inner shaft. This arrangement allows each turbine compressor pair to rotate at its optimal speed. The high-pressure turbine, dealing with denser, hotter gases, can spin at a higher speed to efficiently drive the high-pressure compressor. Meanwhile, the low-pressure turbine spins at a lower speed, matching the airflow and power requirements of the low-pressure compressor. By connecting turbines and compressors in this way, engineers can maximize efficiency and maintain smooth, stable operation across the engine's multiple stages. Next, engineers realize that driving a propeller from this engine could be more fuel-efficient than relying solely on jet thrust. This approach, known as a turboprop, offered better fuel economy, though it came at the cost of lower maximum flight speeds. Next, with more R&D, engineers realized that adding a fan to the engine could improve fuel economy even beyond what propellers offered. And thus, the age of the turbofan was born. Here we see a modern high-bypass turbofan engine. About 70% of the air entering the front fan bypasses the core engine, following the path highlighted by the green arrows. This bypass air flows around the core and contributes the majority of the engine's thrust. Because it moves at a slower speed but with much higher mass flow, it makes the engine quieter and more fuel-efficient than older turbojets. The remaining 30% of the air enters the core, following the path depicted here by the black ducting. Over decades of research and development, engineers have managed to produce very high-efficiency engine configurations. And what we will explore in this sample engine is such a design with a two-stage compressor. First, the air entering the turbo engine passes through the low-pressure compressor, where its pressure is increased roughly 3 times atmospheric, and its temperature rises to around 120 to 170 degrees Celsius. Next, the air enters a high-pressure compressor, which further compresses the already denser air by about 15 to 20 times. Accounting for compression already achieved by the first stage, the overall exit pressure of the compressor reaches approximately 30 to 60 atmospheric, with the temperature rising to 500 degrees Celsius and above, preparing the air for efficient combustion. After compression, the high-pressure air enters a diffuser, which slows it down slightly, converting some of the velocity into additional pressure and ensuring a steady flow into the annular combustor. As a side note, the word annular comes from the Latin annulus, meaning ring. We can see that the cross-section of this combustor is indeed ring-shaped. It forms a hollow section between two concentric tubes. Inside the combustor, fuel gets injected through nozzles and ignited within the perforated liner. These perforations or holes carefully mix air with fuel and maintain a stable flame, even under the high-speed airflow. The hot, high-energy gases then expand through the high-pressure turbine and subsequently through the low-pressure turbine. This staged energy extraction ensures that both the core and bypass streams operate efficiently, providing thrust while minimizing fuel consumption. In jet engines, the turbines operate under extreme conditions, with temperatures exceeding 1,500 degrees Celsius, hotter than the melting point of the metal itself. To survive this, engineers route a small fraction of compressed air from the compressor through internal passages in the turbine blades, keeping them cool. On top of this, advanced thermal barrier coatings and superalloy materials protect the blades from heat and corrosion. Over the decades, jet engines have evolved dramatically. Early turbojets relied solely on core exhaust, while low-bypass turbofans added fans to improve efficiency. Today, high-bypass and ultra-high-bypass engines dominate commercial aviation, featuring larger fans, higher bypass ratios, and optimized blade cooling. Some even use geared turbofan designs, letting the fan spin slower than the turbine for maximum efficiency. These innovations together reduce fuel consumption, lower noise, and increase thrust, a remarkable journey from the first simple jet engines to the sophisticated power plants we rely on today. And that brings us to the end of this video. If you did enjoy the content or found it informative, do give us a like, subscribe, share, and leave a comment. And see you in our next video.